I'm Tamsin Edwards. I'm a climate scientist. I'm a senior lecturer in physical geography at King's College London. Welcome to my exp. I find Greenland and Antarctica really fascinating because they encapsulate some really important parts about climate change. We don't think about the ice caps maybe that much. We think of them as something very remote, something very ancient, which they are, but they are such key parts of our climate system, and the way that climate change is affecting them will last for many generations of humanity. So even if the impacts of sea level rise are slow to come about over decades and hundreds of years, the loss of the ice sheets or parts of the ice sheets will take millennia to replace. And that's a really profound consequence, I think, of climate change. Even if we can adapt to extra coastal flooding, even if we move away from the coasts, even if we think we can live with that sea level rise, the loss of the Greenland ice sheet or the West Antarctic ice sheet is something that I think would be hard to forgive ourselves for, if you like. Well, the two ice sheets of Greenland and Antarctica are quite different from each other. They're affected by the climate in different ways. Greenland is much more of a straightforward case of what we think of when we think of melting ice. Greenland is a really big block of ice sitting up in the northern hemisphere. And the way that it's affected by climate change is mainly, we think, through the warming of the air over the ice sheet, having a direct melting effect on the surface. And there are impacts from the ocean as well. That does have an effect. But primarily it's really about the balance between the melting at the surface and any snowfall that's occurring, particularly in the centre of the ice sheet where it's colder and higher up. So that's a much more standard way of thinking about melting ice, if you like. Antarctica's more complex. It's still affected in those ways of a surface melt and of the balance between that surface melting and snowfall. But what's much more complex and worrying about, particularly the western part of the Antarctic ice sheet, is how the ocean is affecting it. Now, the ocean around Antarctica, the Southern Ocean, it's warming directly because of human activities, but also there's a warm body of water called the circumpolar deep water that circulates Antarctica. And for reasons that could be partly natural, partly human, we think probably on balance more human reasons, that warm water is reaching the underneath of the ice sheet, where it under the ice shelves, and it's having this, it's kind of eroding the ice from underneath, and that erosion then leads to the glaciers that flow into the ocean speeding up in a process that could be a sort of a self-sustaining process. So if we are melting the ice sheet from underneath and the glaciers then speed up, there's this idea that it could form an instability. So it's been called the marine ice sheet instability, where that process becomes self-sustaining and we lose more and more of the West Antarctic ice sheet because of this ocean effect. And it turns out that process is sort of complex. It's a bit more difficult to predict what's going to happen, when it's going to happen, if it's maybe even already underway. And that's a process that would be difficult potentially to stop once it's underway, even if we cooled the climate back down. So if you like, Greenland is more of a standard, you warm the air up, the ice melts, and if you cool the climate back down again, that melting will slow down or stop. But the the impact of the Antarctic ice sheet is really much more of a wild card. It's really something that is harder to predict and potentially could have much more serious consequences. It's important to think about computer modelling, of climate modelling in quite a nuanced way, because at the core of climate models, of models of Antarctica and Greenland, we have some really key certainties. So we have physics that we've known for, sometimes hundreds of years, and we have physical laws and relationships in the natural world that have been incredibly well studied, whether it's through observations, whether it's through lab experiments, field work and so on. And so there are these really secure foundations to how computer models will predict the future of climate change. And it's really important to know how certain those are. But at the same time, there are always going to be gaps. And some of that is gaps in our understanding, because we don't yet know exactly how things work. And some are gaps because computer models always have some limitations. So we can't, for example, simulate every tiny detail of the Earth system. We couldn't simulate every molecule of air in the atmosphere. We couldn't add every fish in the ocean, every worm in the soil. We have to have a certain amount of simplification in our computer models, and we have to have for example, a simplification of scale. We might have a big region where things are sort of averaged. We don't have all of the fine detail, for example, at the meter scale, or sometimes even the kilometre scale, but it could be tens of kilometres or even more.